Hi there, welcome to lecture 28 of Fox, the last lecture. Okay, so let's have some fun discussing efficiency. Okay, we're going to talk about the class P, polynomial, the class NP, which is not non-polynomial. It stands for nondeterministic polynomial. Wow, fancy words. Okay, and then we'll touch on this famous concept called NP completeness. Okay, now, before we get going, let's have a quick recap of last lecture, because that was the punchline of the course, the blockbuster lecture on the theory of computing. So we introduced this Turing machine, okay? And it turns out it's a very powerful machine. In fact, a Turing machine can be constructed, which we call the universal Turing machine, that can simulate any other Turing machine. So it takes that Turing machine's description as input together with, a string W, and then simulates the operation of this Turing machine M on the input W. Okay. Now, the moment you're able to construct such a powerful universal Turing machine, it actually opens the door to very many unsolvable problems. And what we discussed last time was that, certain problems like, the domino puzzle, the ultimate debugger or the halting problem, the program verifier, none of these problems can be solved. And no, in this case, means no. It's not that I can't solve it. It's not that you can't solve it. It's not that the Martian can't solve it. It cannot be solved on a Turing machine. Okay. And so we have this notion of what is solvable. What is a computing problem that's solvable, is a decidable computing problem, and a decider, a Turing machine that always halts and outputs yes or no, captures the intuitive notion of an algorithm. So that completes our discussion on what can and what cannot be computed. Our model of computing is a Turing machine, okay, a decider, a Turing machine that always halts. That's what we mean when we say we have an algorithm. Okay. And then a problem is a language, a set of finite binary strings. Okay. And the goal of an algorithm is to take an input and say yes or no, does it belong to your set? Okay. And if a particular language or a particular computing problem can be solved by a decider, then that problem is solvable, and we say that it's computable. Okay. But then there are problems which we prove that are not solvable, so those are not computable. So it's a little bit depressing that there are all these great problems that we cannot solve. But in some sense, we might have expected it. We can't solve everything, okay? And so what's the path forward? The path forward is to focus on the problems we can solve, on the decidable problems. And so I'm just going to give you a little bit of a tour through a typical curriculum in CS, and of course, we begin at Fox. Okay? And what did we learn in Fox? So we started with discrete math, but then we talked about the theory of computing. And what was the theory of computing? Well, we started simple. We defined what's a computing problem, but then we started simple with the DFA, which is regular expressions, which can solve regular expressions. We talked about context-free grammars and parsing, and then we ultimately came to the Turing machine. Okay. Now, in discrete math, we talked about a lot of stuff. We talked about proof techniques, recursion, sums, number theory, graphs, counting probability. So that's basic discrete math, and we use some of that in the theory of computing. There is other math, like graph theory, linear algebra, probability theory, multivariate calculus. There's a whole bunch of math that's useful in computer science. Okay, now that we have all that, let's say math and the theory of computing, where can we go from the theory of computing? Well, as I said, we now should start focusing on what we can solve now that we understand what we cannot solve, what's unsolvable. Okay, and really, this means that we need to focus on not just what we can solve, but how quickly can we solve them. So now the next issue becomes how quickly can we solve them? Can we solve them fast, i.e. polynomial? Can we not solve them fast, i.e. it requires exponential time? It turns out that there's a fuzzy boundary between fast and not fast. Okay, and that's related to this concept called NP. Okay, so studying efficiency would sort of be the next step in the theory of computing, and if you really want to understand these concepts of P, NP completeness, read chapters 28 and 29. Okay. Now, in terms of courses where you would go from sort of a Fox-like theory of computing, you might take a computability and complexity course, to study in more detail what is computable, and complexity means how quickly can we compute those things that are computable. And you will indeed take a course in some kind of intro to algorithms course. Okay, fantastic. Okay. But in general, we can sort of break computer science into sort of two big parts. The purple part here is theory, algorithms, and AI, and there's a lot of stuff there. Okay, there's this the theory of computing, algorithms, and there are all kinds of algorithms: approximation, randomized, distributed. There are applications to cryptography, to data like machine learning, vision, graphics, finance, okay, to networks. Okay, Okay, computers, social networks, data networks like the internet, robotics, security, programming languages, program analysis. There's a lot of theory and algorithms that's going on in this purple bucket. Okay, and all the math that you learned and the theory of computing comes to play in that bucket. So if you're interested in theory, algorithms, AI, there's a lot of, there are a lot of paths to move forward, and there's a lot of stuff that will be used. Okay. On the other hand, you might be interested in software and systems, and it depends on what part of software and systems you're interested in. Are you interested in the sort of program analysis, programming languages, networks, robotics, security side, or are you interested more in developing systems like database systems, parallel computing, operating systems, architecture, and so on and so forth? Depending on what your flavor of software and systems is, you'll make use of grammars, DFAs, all the various kinds of math, induction, recursion, graphs, probability, and so on and so forth. So in some sense, you can't really escape the foundational math and the foundational theory of computing. It is really embedded into the rest of the curriculum. Now, depending on what your flavor is, you might emphasize, one over another. You might emphasize theory and math over software and systems. So that's, sort of a high-level view of where you can go from Fox. Now, where are we going to go in the rest of Fox? Well, we're just going to spend a little bit of time talking about efficiency, something that you will focus on much more in your next algorithms course. A little bit of time focusing on efficiency, but I really want to end on a note, an emphatic note. You'll have to stay tuned for that emphatic note. Okay. So, for the moment, let's go to the board and discuss a little bit efficiency. Okay, so let's touch on the efficiency of Turing machines and the theory of NP completeness. Now, of course, if you want to get more details, read chapters 28 and 29. Okay. Now, to focus the discussion, let's consider a very simple problem. So, the language, which is a problem, computing problem, is 0 to the n, pound 1 to the n. So this is the equality problem. Okay, and let's build a Turing machine to solve this problem. A very simple Turing machine, and I'll illustrate it on tape, okay, on an example. So we have a very simple example. Okay, imagine that we have 0, 0, 0, 0, pound, 1, 1, 1, 1. For good measure, we have a blank symbol here. Okay, and as usual, we have our beacon. Okay, so our Turing machine starts here. Now, how would we solve this problem? And with a Turing machine, it's actually relatively easy to solve this problem. You come and mark this 0, then match a 1, then come back and mark another 0, then match a 1, then come back and mark another 0, then match a 1, mark another 0, match a 1, and then there are no more zeros to mark, and there are no more 1s in here, and so you're done. Okay. So if we look at how this Turing machine moves, you see that it's going to move to here, it's going to move here, and then it's going to move here, then it's going to come back, then it's going to move back. Then it's going to come back, then it's going to move back, then it's going to come back, then it's going to move back, and so on. So it moves back and forth. So if we call this number of bits n, the total number of bits, well, it's approximately, twice the number of zeros. So the number of zeros is approximately equal to n over 2. And so it's going to have to make a zigzag like this for each 0. So it's going to make n over 2 zigzags. Okay. And each zigzag travels approximately n over 2 and n over 2 back. So each of these corresponds. So each time the machine has to move, that's a step. And we can imagine it takes a unit of time to make one step. So each zigzag involves n moves. So a total of n times n over 2 moves by the Turing machine head. So theta of n squared moves, which roughly speaking is the running time. Let's call this machine M1. Okay, so M1 has a running time in theta of n squared. And we're familiar with asymptotic notation. In fact, that's one of the reasons we introduced asymptotic notation, to analyze running time of algorithms, and algorithms are Turing machines. Okay, now, challenge. There exists, it's possible to construct a Turing machine which improves on this, whose running time is n log n. Theta of n log n. So you can, take up this challenge and try to figure out a Turing machine, specifically, an algorithm that would, that has only the basic capabilities of the Turing machine and that runs in n log n. I leave that as a challenge. You can read chapter 28. It has the details of how you could do this. I want to focus on something else. Okay. Supposing now that, I add a twist to my Turing machine. Okay. I add some parallelism. I make the architecture parallel. So I give you 2 tapes and 2 tape heads. Okay. So you can imagine that there's a master tape, okay, with, 0, 0, 0, 0, pound, 1, 1, 1, 1, and for good measure we have the blank symbol to show you that we end the input there. Okay, and you have your usual beacon symbol. Okay, and you have your head for your master head and your first tape, and I give you a second tape. So this is a more sophisticated, more elaborate Turing machine. Okay, it's got more than 1 tape, in particular 2 tapes. It could have more, could have 10 tapes, 50 tapes. I'm just illustrating with 2 tapes. Okay, sorry, blank. These are all blank. Okay, so these are all blank. The input is on your master tape, let us say. And you've got a second head that can move along this tape and a head that can move along that tape. And your Turing machine CPU, your DFA, can control each of these heads independently. Can we solve the problem more quickly? And the answer is yes. And here's the basic algorithm. Take this head and move it right. So at each step you move it, you read 0, and simultaneously move this guy right. Whenever you read a 0, write the 0 here. So you move this guy right. Okay, and every step you move, you read, and then you move this guy right and copy that symbol to here. So essentially you can think of this as I'm copying. So I have 0, 0. I'll end up writing 4 zeros. Okay, so now this guy's head is over here, and this guy's head is over here. This guy's head is over here after the copy. Okay, great. Now I continue moving this guy right, and for every one, while I'm moving this guy right, I move this guy left, and for every one, I check that there's a corresponding 0. If I come to star before I end the ones, there were fewer zeros. If I end the ones before coming to star, there are fewer ones. And if when I end the ones I'm at star, okay, there are exactly the same number of zeros here, which is equal to the number of zeros here, which is equal to the number of ones. So I just go back now. I continue here, and I go back, checking off each one with a 0. Okay, so let's see the number of moves that are made. This guy scans half, then scans half. This guy goes forward and back. So this is n plus n is 2n. Okay, so in theta of 2n steps, which is theta of n, in asymptotic notation, we get rid of these baby constants. I can solve the problem using M2 tape. So M2 tape. You can think of this as a parallel architecture. So parallel architecture, adding multi-threading, adding parallel capability has significantly improved the running time. Okay. Interesting. So maybe I should go to 3 tapes or 4 tapes. Well, it turns out, and you can see the proof of this in chapter 28, it turns out that, 2 tapes, 3 tapes, 4 tapes don't add significantly more capability. Now, the point that and we'll get to that point, okay, but the real message here is to look at these running times and notice that they're all polynomial. They're all polynomial. And why am I pointing that out? Okay, because what I'm essentially saying is that the running time was polynomial on a single tape. Now we can try to improve it, but it's still polynomial. The running time is polynomial on the 2-tape machine, and we can try to improve it. Maybe we can get n over 2, but it'll still stay polynomial. Could we get log n running time with some number of tapes? The answer is no. So you cannot get exponential speed up from going to multiple tapes. You can only get a polynomial speed up. For example, n squared to n. Okay. So theorem. You cannot get exponential speed up from going to multiple tapes. You cannot. In fact, the theorem is a little bit more elaborate. So the theorem says the following. Let's say you have a multiple tape architecture with some fixed number of tapes. Let's say k, for example, 2. Okay. And in your multi-tape architecture, in your multi-tape architecture, let's say the running time is T of n. Okay, then we might ask, what's the best you can get on a single tape? What's the best you can get on a single tape? Single tape, okay, we can show, okay, and this is called the simulation theorem. So single tapes can simulate multiple tapes with at most a squaring slowdown. So if the running time is T of n on multi-tape, then the single tape will have a running time at most O of T of n squared. That's very interesting. Okay, so let me sort of break down what I'm telling you. What I'm telling you is that if you can solve a problem in a parallel architecture, so parallelism, okay, you solve a problem in a parallel architecture, like this, two tapes, okay, you can solve that same problem on a single tape architecture, so no parallelism, and the running time will at most square. So you might think, oh, but squaring is a big deal. Yes. So for example, if this is n cubed, this becomes n to the power 6. Okay. And that's the worst case. Worst case is it can become n to the power 6. Okay. And then you say, yes, in practice we do care. And yes, in practice we do care about the parallel architectures. That's the kind of speed ups they can give you. But okay, in theory, something interesting is popping up. And let me sort of try to convince you that this interesting thing is very interesting. So what it says, okay, is that if your running time on some architecture is T of n, then your running time on the single tape is T of n squared. Okay, let me rephrase that in a way that's going to be more useful. If it's polynomial, if your running time is polynomial in some architecture, then it's polynomial on the single tape. Why? Because it's going to be polynomial squared, and the square of a polynomial is polynomial. Okay, and so this is one of the things that justifies the notion of polynomial as a sought-after property of an algorithm. Okay. We like our algorithms to be polynomial, and we don't distinguish between n and n squared, not because in practice n and n squared are different, but because polynomial is polynomial on any architecture. Okay. So this sort of leads us to define this robust notion of speed. So we say that a problem can be solved quickly if it can be solved in polynomial time. And that motivates the definition of the class P, the class of problems that can be solved in polynomial time. So the class P, the class of problems that can be solved in polynomial time. Okay, and then you would say, but wait a minute, in polynomial time on what architecture? Okay, and that's where this discussion comes in. Doesn't matter. Single tape, parallel. If it's polynomial here, it's polynomial here. If it's polynomial here, it's polynomial here. And that is the extended Church-Turing thesis. It says that, all reasonable definitions of Turing machine, parallel architecture, single tape, can your Turing machine stay in the same place or it must always move? Okay, all various reasonable definitions of Turing machine, they preserve this notion of polynomial. So a polynomial on any Turing machine is essentially a polynomial on the standard single tape Turing machine. Okay, so architecture independent. This means that we have a notion of fast that is architecture independent. And that is why polynomial has stood the test of time. Okay. In order to, if something is not polynomial on my architecture, in order to break that, you can't do it by just going to parallel. Okay. You need something fundamentally new. Okay. So polynomial is architecture independent. Okay. So let me give you an example, some examples of problems that can be solved in polynomial time, and now we don't need to specify the architecture. That's the beauty of this equivalence between various types of architectures and the single tape. If it's polynomial on any architecture, it's polynomial on all architectures. Okay, so let me give you some examples. Okay, network flow. Okay, what's the fastest rate at which I can send packets from here to Washington, D.C.? Network flow. We can solve this in polynomial time. So it's efficient. There are fast Turing machines like these guys, polynomial time that solve, network flow. making change. Make change. So in the US, we've got, the penny, the nickel, the dime, and the quarter. And I might ask, well, I want to make $1.27, 127 cents. What's the fewest coins I need, to make that change? We can solve that in polynomial time. We can solve it very efficiently. Finding the optimal highway system that uses the least amount of material to build roads, but connects all the nodes in a road network. That's minimum spanning tree. So minimum spanning tree. Efficient. Euler path. So how do I plow all the roads while visiting every road once? Efficient. Euler path. Sorting. I give you a list. Can you tell me, is it sorted or not? We can solve this problem efficiently. It's all polynomial. Lots of problems that we like to solve in practice, and we can solve them fast in polynomial time. So that is the class of problems that we call P. The class of problems that can be solved in polynomial time. Well, are there problems that we cannot solve fast? So remember, now we're only talking about solvable problems. Problems that can be solved by a Turing machine decider. So are there problems that we know cannot be solved fast? Yes, we call those problems exponential problems, or EXP. Cannot solve in polynomial time. Just cannot. We can prove it. What are examples of this? So most complex games that involve multiple complex strategies and multiple ways, in many ways in which the game can flow, so exponentially many such ways, are provably non-polynomial. For example, chess. What would it mean to solve chess? So to solve chess, it means I give you a board position and I say, who wins, black or white? So you say yes if it's black, you say no if it's white. So such games typically cannot be solved in polynomial time. So they are in exponential. They're in the class of problems which we call exponential, or EXP. Not ESP, EXP. You can't solve them with ESP. You can solve them with algorithms, but those algorithms take a long time. Exponential time. So there's a boundary. We can call this boundary, let's put this boundary here. And every problem is either solvable in polynomial time or not solvable in polynomial time, in which case it requires exponential time. But now here is the problem. In theory, every problem either belongs above the line or below the line. In practice, and also in theory, there are many important problems for which we don't know which side of the line they belong. So this boundary isn't a thin line, it's a very fuzzy, thick region. So this boundary is a fuzzy, thick region. And what do we mean by that? So that's what we're going to discuss. So, what are these problems in this fuzzy, thick region, which I'm saying that we don't know whether to put them in P or in X? Let me give you some examples. So remember that problem half sum. Half sum. I give you a set and I ask you, is there a subset whose sum is a half of that set, of the total sum? Half sum is in this set. And many interesting problems are in this set. So let's go through some of those interesting problems. Clique. So I give you a graph and I say, find the maximum clique, or clique being a set of friends who are all mutually friends, or is there a set of 25 friends who are all friends with each other? We don't know how to solve clique quickly. We don't know how to solve it quickly, and we don't know whether it can be done. That's what's tough. Dominating set. So dominating set. So the problem is place hospitals at intersections so that nobody has to travel more than one hop to get to a hospital. Vertex cover. So place policemen at the intersections so that each policeman will surveil the roads that come to the intersection. What's the minimum number of policemen you need? K-center. You have a budget of 10 McDonald's. Where do you want to place them? And the idea here is that nobody should have to travel too far to get to a McDonald's. Because then I make more money. If a McDonald's is next to me, McDonald's will make more money because I'm continuously going to be going there and eating chicken nuggets. Okay. And there's another problem that's in this region, okay, which is the matching subsets challenge problem. Okay. So it doesn't mean we can't solve the matching subsets problem. It just means that we don't have an algorithm that, for no matter what the input, will guarantee running in polynomial time. So we don't have a fast algorithm. It's possible to solve this problem, we just don't have a fast algorithm. Okay. And even worse, we don't know if one exists. So this region, all these problems sit in this region. Okay. And this region is fuzzy because we don't know how this region lies with respect to this line that divides slow from fast. So are these problems in fast or are these problems in slow? Fast means polynomial. Okay. And so that's what I'm going to discuss. And that's what is very interesting. This region of interesting problems, okay, we don't know whether they're fast or slow. They are either fast or slow, every one of them, but we just don't know. Okay. So let's take as an example half sum. And I want to show you something interesting about half sum. So half sum, let's consider the set S is 1, 1, 3, 5, 7, 9. So the sum here is 26. Okay. So half sum would ask, is there a subset which sums to 13? So if I take the subset A, which is equal to 1, 3, 9, so that's a subset, and the sum is 13. So this is the sum of S, and the sum of A is equal to 13. So half sum in this instance of the problem is true. So there is a subset whose sum is half of the total sum. Okay. Now, for the general instance where I feed you this set as input, can we come up with an algorithm to answer the question correctly? And if the answer is yes, then can we produce this set A? We don't know. We don't have a polynomial algorithm to do that. Now you might think, wow, this is such an easy problem. Well, go for it. You think it's an easy problem? Go for it. Try to come up with a polynomial algorithm to solve half sum in the general case. If you do, not only will you be famous, you will also be rich. There's $1 million riding on that. And that has to do with what I'm about to discuss. It's not this meager $100 that I was offering. $1 million if you could solve matching subsets in the general case. I was just asking for a special solution to the 100 numbers that I posted. But if you can solve matching subsets in the general case, famous, Turing Award, $1 million. Okay, now what's interesting about this problem? So what's interesting about this problem is I don't know how to solve the problem, but let's say you solved the problem and you came to me and said, the answer is yes. Okay, and I say, what? I don't believe you. Prove it to me. So prove it to me. Prove to me the answer is yes. And so you come and you say, my proof is the set A. Okay, and I look at this proof and I say, okay, let me check your proof. So I add up all the elements in A. That's the sum of all the elements in A is 13. So I add up all the elements in A. The sum is 13. And then I go and add up all the elements in S, and it's 26. And I check that 13 is half of 26. And I say, okay, yes, you're right. Your proof works. Okay. Now, what's interesting here? What's interesting here is that I don't know how to solve the problem efficiently. You solved the problem somehow, and then you came up with the proof, i.e. the set A. And what was interesting here is that it was easy for me to check the proof. Easy means I can do it quickly. How long did it take me? If the set S has n elements, then I compute this sum is n, and I compute this sum, which is at most n elements, or at most n, so at most 2n operations, or at most 2n additions. So it took me order of n time to check the solution. So if you find the solution and a proof, then it's easy, i.e. polynomial time. So it's easy, i.e. in polynomial time, it's easy for me to check the proof. Sometimes we say that you are the prover and I'm the verifier, or not sometimes, I'm typically called the verifier. Okay, and the proof you gave me, this subset A, this proof is sometimes called the certificate, the proof. Okay? But the basic idea is you gave me a proof and it was easy for me to check the proof. Okay? And all of these problems are, in that flavor. That, we don't know how to solve them quickly, but if someone solved it quickly and gave me the proof, for example, like the subset A, or if someone solved the problem, I asked, is there a clique of size 55 in this graph, in this Facebook network? So you come to me and say, yes, and my proof is a set of 55 nodes. It's easy for me to go and check if all of those nodes are friends with each other. So it's easy to check the proofs for all of these problems. And that's interesting. We don't know how to solve them, but if someone solved it and gave me the proof, it's very easy for me to check the proof. Okay? So let's summarize that. It's easy to check the proof. Okay. And it turns out that all the problems in this region that we are fuzzy about satisfy this condition. And so we've given this condition a name. Okay. We call all these problems that satisfy this condition, where if you find the solution and find a proof, then I can quickly check the proof. We call those problems NP problems. So we call that set of problems NP. And you might say, what? What does that mean? So I'll tell you what it means. It stands for non-deterministic polynomial. Okay. And this is a very technical name. It amounts to the statement that for these problems, if you solve them and give me the proof, I can check the proof quickly. Okay. And now let me explain to you a little bit about what this non-deterministic polynomial means. Okay, so remember I told you there's the single tape architecture, then there's parallel tape, let's say 500 tapes. Okay, and you might have remembered I mentioned when we discussed sort of CFGs and DFAs with stack, I said that CFGs are slightly more powerful than DFAs with stack. Okay, and in order to make them equivalent, you need to give the DFA a slightly higher capability, which is what I call non-determinism. So the non-deterministic DFA with stack is as powerful as C context-free grammars. And the same sort of thing is going on with Turing machines. So you have the single tape, you have, let's say, parallel tapes, let's say 500 or 1,000, but some fixed number of parallel tapes. There's one other architecture, but it doesn't fall into this class, and that architecture is, in some sense, unbounded parallelism. So unbounded parallelism. That, in sort of a gross nutshell, is sort of what non-determinism allows a machine to do. It allows it to try all kinds of possibilities simultaneously. Some kind of unbounded parallelism. Parallelism, just, if I have 500-fold parallelism, I can try 500 things simultaneously. Unbounded parallelism allows me to try, many things as I want in parallel. Well, so it's unbounded parallelism. So this is what non-determinism is. Now, in the context of what we can implement in practice, we can't implement non-deterministic Turing machines. So they have not much practical value, but they have theoretical value because this level of this kind of architecture, this kind of non-determinism exactly corresponds to problems who, if you can solve them quickly and find the proofs, then we can easily check the proofs. So that's a very intuitive definition. This is the technical definition. Those problems can all be solved in polynomial time. So the polynomial, those kinds of problems can all be solved in polynomial time on a Turing machine with this kind of capability. On a Turing machine with non-deterministic capability. Okay. Unbounded parallelism. Now you might think, well, if parallel is equivalent to single tape, then shouldn't unbounded parallel be equivalent to single tape? Turns out we don't know. Okay, so polynomial on parallel is polynomial on single tape. Polynomial on unbounded parallel, i.e. polynomial on non-deterministic machine, is that equivalent to polynomial on single tape? We don't know. So, if you can solve in polynomial on this non-deterministic Turing machine, is it equivalent? Does that mean that there's a polynomial algorithm on the deterministic, on the single tape Turing machine? We don't know. And that is the famous question, P equals NP. P, we can solve in polynomial time on the single tape machine. NP, we can solve in polynomial time on this weird machine that has unbounded parallelism, on this non-deterministic machine. Question mark. Is P equal to NP? We don't know. You solve that, instant fame. $1,000,000. Okay. And that's going to be, and solving this is related to something that I'm now going to discuss, which is the structure. So it turns out that these problems whose proofs are easy to verify, these problems have a very nice structure. Okay. Have a very nice structure. It turns out that inside here are some problems which you can consider to be the hardest problems in this fuzzy region. Okay, so there are, you can think of these as beacon problems. So there are these starred problems which are the hardest problems in this fuzzy region, corresponding to computing problems which we don't know how to solve efficiently. But if you solved and gave me the proof, I can check your proof very efficiently. Okay. And what does it mean to be a hardest problem? So you can think of this guy as a hardest problem. So this set of problems is called NP. So a hardest problem in NP. Okay, so there are these hardest problems in NP. And what does it mean to be a hardest problem in NP? Well, if you figure out a way to solve this problem in polynomial time, then every problem in this fuzzy region can be solved in polynomial time using your solution as a subroutine. Okay. So if star is solved in polynomial time, then star can be used as a subroutine to solve all problems in NP in polynomial time. So let's pause and let that sink. So here's the hardest problem in this fuzzy region of problems, which technically are defined as NP, and at an intuitive level are defined as problems whose proofs are easy to check. So if you claimed a solution and found a proof, I could easily check that your proof verifies your solution. I can easily verify a proof. So there's this hardest problem. If you give me a polynomial algorithm for that hardest problem, a polynomial Turing machine on my usual single tape, then I can use that algorithm you gave me as a subroutine to solve all of those. What does that mean? That means that if this hardest problem is polynomially solvable, then all of them are polynomially solvable. Okay. If this hardest problem is polynomially solvable, then all of them are polynomially solvable. These kinds of hardest problems are called NP-complete. So this kind of a hardest problem is called NP-complete. Wow. And the study of these problems is the theory of NP-completeness. Wow. Okay, so there are these hard problems. And what's nice about these hard problems is we don't know where this line goes. So all these problems, we don't know whether they go into the class P or into the class X. But if one of these hardest problems, we can figure out that this hardest problem, let's say, is in P, then this line automatically moves down here and all the problems are in P. Wow, we can solve all these problems and show they're all in P by just studying the NP-complete problems, or even just studying one NP-complete problem. It turns out that all these problems are hardest problems in that fuzzy region. So you might think, really? Half sum is a hardest problem in this fuzzy region? Yes. If you can come up with a polynomial algorithm for half sum, instant fame, $1,000,000. You will have proved that P is equal to NP. Okay. So, when it comes to efficiency, you have the single tape Turing machine. From the perspective of what can we solve quickly, so fast Turing machines, if you have a single tape Turing machine, or if you have multi-tapes, so parallel architecture, fixed parallelism, polynomial is polynomial. And so we define this class of problems which are polynomial. Okay. And the definition of a polynomial algorithm, or the definition of a polynomial running time for a Turing machine, does not specifically determine or depend on the specific architecture, how many tapes, how many heads, and so on and so forth. Now, in practice, yes, we do care about the difference between n to the sixth and n cubed. But in theory, polynomial is polynomial. So there's a fundamental divide between exponential and polynomial, and this divide has withstood the test of time. Algorithms that are polynomial, we can use them in practice. Algorithms that are exponential, there's no hope to use them in practice. And now we see a theoretical justification for the robustness of polynomial. It's architecture independent, except if you have an architecture that has unbounded parallelism. If you're polynomial in such an architecture, we don't know if you're polynomial in the regular architecture. Although we don't have machines that have unbounded parallelism, so it's a theoretical question. Or, from the more practical perspective, problems whose proofs can be verified quickly, we don't know if those problems can be solved quickly. Okay. And so that is sort of the whole definition or the discussion around the set P, the set NP, and whether or not P is equal to NP. It's trying to figure out what's going on in this fuzzy region between slow and fast. In theory, all these problems either belong to P, they're either fast or they're slow. Okay? And an NP complete problem holds the key. If you can show that an NP complete problem is fast, all this region becomes fast. And the line drops here. Everything in this region is fast. Okay? So that's a little bit of a glimpse into sort of what we call complexity theory. Okay? So the theory of, how quickly solvable problems can be solved. Okay? So now I want to erase, and that more or less marks the end of the course. I want to erase and end on an emphatic note. And so because it's an emphatic note, I'm going to erase. So here's my emphatic note, and I'm going to end with, a couple of quotes from some famous people. We started the course with the first quote by Dijkstra, which basically says that, this high technology that is so celebrated today, i.e. the computer, is essentially a mathematical technology. And then, the second quote is, to err is human. So we're all going to make errors now and again. But to really foul things up, you need a computer. Okay. Now, So just bear these two quotes in mind, in your future career path. And I want you to take the role of a programmer, for example, or writing computer programs or writing algorithms to solve problems very seriously. Okay. And in order to convince you to do that, I have listed, a whole bunch of disasters, okay, that have occurred in the past. And they are primarily due to, computer algorithm malfunctions. And I'll go through a couple of them. Okay. One of the interesting ones is sort of in 1983 when we almost had World War III. Okay. So, the Soviets had some, automatic missile detection system to detect missiles coming from the US. Okay. Now, it turns out that the clouds, so what does this detection system try to detect? It tries to detect metallic flying objects that are flying at, incredible speeds towards various cities in Russia, like Moscow. Okay. Now, it turns out that on a particular day, okay, the clouds were such and the reflections were such that, everything looked like metallic things flying through the sky with all these various reflections. And so the whole system went into red alert mode, red alert. And the way it was geared was, when this happens, we're going to fire back. And if that had happened, boom, it would have been World War III because there were no missiles coming from the US. Okay. So, the operator, the guy sitting there operating, was thinking to himself, what? Could this be? Surely Russia is worth more than 5 missiles. So the system had detected 5 missiles coming over and he's thinking, no, if the Americans are going to attack us, they're going to use more than 5 missiles. We're surely worth more than 5 missiles. So he didn't pull the trigger because of that gut feeling that, 5 missiles doesn't sound right. Okay, imagine. Software bug. Well, it's not that it was really a software bug. You've got to be careful. You've got to test all the boundary conditions. You've got to prove that your system works. The Therac 25 was a radiation therapy machine, and it gave sometimes by accident, by concurrent programming errors, it gave 100 times, 1,000 times the necessary dose of radiation, in some cases killing patients. Software bug. Okay. Tesla self-driving car. Failed, quote unquote, failed to detect a truck, and so crashes in, 1 person dead. Okay. And the interesting ones that are going on these days, and it's not like they're super rare. So the most recent example of an airline disaster is this Boeing Max fiasco, okay, where, roughly speaking, 346 people dead. Okay.
So what was the problem there? It was, it was an issue with the attack sensor and signals coming in that were not correct, but the algorithm couldn't figure it out. So algorithmic issues, okay, that resulted in 346 dead. So, I'm not saying that we are killing these people. What I'm saying is that, software is everywhere. Programs are everywhere. Okay? And when programs go wrong, real serious issues occur. People are dying. Money is lost. And it's estimated that in the US alone, approximately 60 billion annually is wasted on either rewriting code or fixing code or productivity loss or actual damages due to software errors. Okay? But that's monetary. On the flip side, forget about monetary. People die when software makes errors. Okay? So, this class has been all about rigorous proof. Okay? And so I'm urging you to take the time and the effort to prove that your program works fully correctly all the time. Okay? Partially correctly, missing a few boundary cases, people die. Doesn't work all the time, accident. Okay? So the only way that you can be sure that your program works fully correctly all the time is if you can prove that it works. Can you convince me that your program works fully correctly all the time? Take the time to do it. It's worth it. It's worth the effort because people are relying on it. Now, with that, we have the tools to do those things. So use them. That's the happy note. We have the tools now to prove that programs work fully correctly all the time. Use it. Checking out, not just from this lecture, but from the course. Good luck.